Hey guys, this is Andrew with HKN, and today we're going to be talking about the intro to the optimal coherent receiver, and in general, all optimal coherent receivers. So, a receiver is something that takes, in general, when we talk about digital communication systems, we use finite length signals, which means that signals that don't go on forever. They have like a period, usually called T, that they exist for, and we use them to represent some symbol. Well, what's a symbol? Well, a symbol can be really anything we want to represent in our digital communication system. Some examples of this could be letters like ABC. They can be strings of binary numbers or even a single binary digit. So for instance, like 00, the three-bit sequences that I've written here. Or they could be some combination of letters and numbers like I have here. Or they could really be anything. They could be the weather outside. They could be current traffic conditions. Literally anything you want to represent and send. So once we know that that's how we're going to deal with it, we want a receiver that minimizes the errors on the other end of some channel. And what that means is that we have a sender, say over here, and we have a receiver over here. Well, there's some way that we get signals, say S1, S2, and so on and so forth, over to here. And hopefully, we want the difference between what we get at the receiver and what we get at the sender to be as small as possible. We want that difference to be as small as possible. The whole idea of what I mean when I say the difference between them can be a little bit confusing, and we'll formalize those in the later videos that we're going to talk about on this subject. But in general, what we see is that we want to send something over to this receiver, but on the way over, there's going to be, it's not perfect, there's going to be some corruption. There's going to be some noise added in here. And in fact, this is what we call an additive white Gaussian noise channel. And we'll talk more about that later. But specifically, this is the kind of channel we're going to see where we have a set signals that we're going to send, and we have a receiver. The difference between this kind of communication network and ones like, say, on your FM radio or your AM radio are that in analog communications, remember this is for digital communications, analog communications, we have continuous time signals that we're trying to send, like a voice, something like this, where the value at any point in time could be any of an infinite number of numbers, right? It could be any real number, unless you've capped the network somehow, but still, there's an infinite number of possibilities if we look at any point in time what this value could be. And so that makes it a little difficult to get exactly what we sent, and makes our error a little bit larger in some sense. But in digital communications, what's nice is we have a finite, what's called an alphabet. So it kind of makes sense because in our English alphabet, we have a possibility of 26 letters that we can send, 26 letters that we could use. So we know if you use an English letter, that it's one of those 26. So that means that you're never going to guess it's the letter, F-E or whatever. There's no letter that. It's either a letter A, B, C, D, so on and so forth. And that's kind of what we exploit in digital communications, is that we know we have a finite alphabet. So say the set of binary numbers of length 2. So we send these guys as signals. Say I say that this is something like, a straight line. This one is a straight line for half the time. This one is a negative straight line for half the time. And the last one is a negative straight line for the full time. These are examples of ways that I can code these. And if these get corrupted in some way, well, I don't have an infinite number of possibilities to take these to. I know for a fact that I only sent one of these 4 signals. So that can allow us to, in fact, just make a decision on one of these four and use that to try to minimize our error even more. And that turns this receiver problem into what's called a decision problem. So all we really want to do is decide which one of these was sent based on what we received. And in order to do so, we're going to use something, we're going to use a couple of different philosophies that we can use. They're called MAP, ML, and MD. MAP stands for maximum a posteriori. ML stands for maximum likelihood. And MD stands for minimum distance. So the use of the words maximum and minimum make you think that we're going to be doing some calculus. And in fact, we are. We're going to be maximizing and minimizing things. And what we're maximizing and minimizing is going to be a probability. And we'll talk more about that in our videos on the optimal receiver for the decision part. That comes at the end of the series here. But before we get to that, we need some background information on how we're going to form these different receivers, which are called MAP, ML, and MD receivers. So first of all, we're going to talk about how we can represent signals in a discrete way, how we can represent them as just, integers, or a group of integers, let's say. Represent these continuous time signals as a group of integers. Then we're going to talk about orthonormal basis functions and the Gram-Schmidt process. That'll make more sense if you watch the video. Then we're going to get into the optimal receiver, and we're going to talk about something called signal space. Basically, the space that all of the signals that we could possibly receive here can occupy. And all of these are related, and they build on each other, so I suggest you watch them in order. And then finally, we're going to talk about the optimal receiver and how we decide which one of our alphabet we have sent. I suggest you watch these in order, and I hope you watch all of them. I hope they're helpful. So let's get started. Move on over to discrete signals, and hope you guys learned something. Have a nice day.